Excellent, and good morning, everyone. So yeah, I'm very happy to give a presentation here, and since it's at the beginning of the conference, I'd like to not dive into ELT instruments immediately, but start with a general introduction and overview, the challenges we have that apply to essentially all instruments in the mid-infrared, and then also focus on the specific challenges to transfer that knowledge from 4-meter, 8-meter class telescopes to ELTs. Then at the end, I would like to discuss METIS and MICHI a bit more in detail. And so I have covered part of a talk that Chris Peckham was planning to give, and I think now it's a condensed version, and that is to everyone's benefit. I should also give a credits to the METIS team. You see their images at 10 microns taken on the right, as well as inspirations from the last Lawrence Center workshop. When I refer to mid-infrared here, I essentially mean both thermal infrared and mid-infrared, so anything alongward of K-band or 2.5 microns going out to Q-band, okay? So let me start, or maybe I can use a laser pointer here. Let me start with the general mid-infrared challenges, and of course, you know, we talk about sensitivity, background, and angular resolution. So if we look at the sensitivity of the instrument, and here is shown point source sensitivity in millichansky's, just normalized to 10 sigma. So you will see there are I picked randomly 3 instruments here representing an interferometer, an 8-meter class telescope, and a 4-meter class telescope. And there is a clear sensitivity gap between those and even instruments on an 85 centimeter telescope in space, or what we hope will launch very soon on the James Webb Space Telescope. So, and this is of course one of the unfortunately defining limitations of our field. So I think there's one of the problems when you dream of high redshift galaxies for the near future. It is still, I think, at least remains a dream, and but that doesn't necessarily compose a fundamental problem to the field, and I will tell you why. Okay. So, of course, the background, Cora referred to it already. Now I don't have it for different atmospheric conditions. I just have a computation here that was done for METIS on the ELT at Cerro Armazones, showing in black the total emission of the background, which is then composed of the cryostat window, the telescope, and the sky. And what you can see here, of course, is the window is not negligible. But of course, the telescope itself is an order of magnitude above that. In most of the atmospheric windows, like here at 10 microns or so, you can see that except for discrete spectral features, and I have indicated here on top the most dominant species here that affect the transmission, which is the background, which is water, CO2, and ozone. And what you see here is that, of course, in the atmospheric windows, the telescope is the biggest offender, but of course, at the edges of the bands, the atmospheric transmission is very important. So it's a very delicate thing. It would be great if we would find ways to collect photons without using a telescope. Okay, so if this were the whole story and the whole background would be constant, okay, I think it would be easier to calibrate it, but of course we have to deal with many things. We have to deal with detector instabilities, which are usually at relatively short frequencies, the atmosphere, and maybe non-equilibrium or thermal drifts of the telescope. And that all leads to a background structure that is variable on different timescales. Here is an 1 minute exposure, total exposure of the VLTI MIDI pupil. But I also have a movie for you, and I think I need to deactivate the laser pointer to get it started. So here you see a time series of MIDI chopped different frames. So it's the chop difference already. And the point here is, of course, that the emission is A, not uniform, and B, highly time variable. Yeah, and this is, of course, if you add up all the images by just co-adding things, then of course you also add up more noise possibly than you would like to have, and these are things we have to do. Okay. Now, what can I do on Monday morning? For some of you, it's just past midnight. I thought I'll ask a very fundamental question from maybe experimental astronomy 101, and it's just a test to see if you're still, if you're already awake. So we've set up a poll in Zoom, and I would like to ask you to participate all. It's just pick the right answer because, oh yeah, is that clearly visible there?
The poll should be visible for everyone now.
Okay, okay, good. So it's an anonymous poll. So just please pick an answer and you will not be punished and we will not know who gave the wrong answer. And I think, Leo, you can also share the results with us, can you?
Of course. People are slowly waking up, 20%. 30% have voted. Let me give it 10 more seconds. 60%. Okay, your last chance, 5 seconds. All right,
okay.
7%. So this is the result.
Okay, now this is a very interesting result. Okay, so most of you believe it's d squared, and I would be delighted if this were the right answer. Unfortunately, it's not, and the argument goes as follows. So this is, consider a point source on, let's go back to the laser pointer, consider the point source on a background for a small telescope, and it's Nyquist sampled. So what will happen? Your source flux increases, of course, as the telescope collects more power with d squared, the background as well, and the noise is the square root of the background. So you have, if you just look at the telescope, you would have an increase proportional to d. But at the same time, you adjust the pixel scale of your instrument so that your Nyquist sample to the diffraction limit, and then you keep the source flux, but you reduce the background because you have a smaller pixel field of view. And so you get another signal to noise increase of d. So this is for point sources. Now, if we have an extended source, then we have the same scaling for the telescope aperture, right? So we increase the signal to noise with d if you go larger telescope. But if we keep the diffraction limited pixel sampling, then of course we also get less from the source. So the signal to noise with smaller pixel scale for a uniformly extended source decreases with the telescope diameter. And these two effects cancel, and in other words, the signal to noise per pixel is constant. So in other words, you will not get more extended source sensitivity per pixel if you use the ELT instead of a 4-meter telescope, and that of course sucks. So you would gain sensitivity by resampling, but this is one of the main problems why whenever we look at extended sources, we're far inferior to space missions. Now, of course, where I think we can make very important contributions is, of course, for compact sources and point sources. And this is essentially the same plot we showed before with the point source sensitivity in Millichansky, but now I plotted on the y-axis the angular resolution. I put the instrument there again, and of course, METIS is fantastic as a VLTI instrument for angular resolution, maybe not so for sensitivity. IRAC, the infrared camera on Spitzer Space Telescope, is very good in terms of sensitivity, but bad in angular resolution. And what would be interesting, let's say we take 1 AU at 10 parsecs, so this gives us an angular resolution of about 1.1 arc seconds, and here I've added some fluxes taken from the literature for beta peak, for well, famous nearby planets. And what you can see here is, of course, this is the region we want to be at in terms of angular resolution and sensitivity. And clearly, this points toward using an ELT if we want to get into that range. Okay, so Now, let me go to the second part of the talk, namely general considerations for ELT instruments. And I mostly talk about ELT and the TMT here. I neglect the GMT, and that's simply because this is a conference in mid-infrared astronomy, and the TMT instrument, the GMT instrumentation program there isn't really overwhelming. Now, what people need to be aware is that if you just the construction and operations cost of the ELT, that gives you about 500 euros per minute. That's what your observation time costs, right? So I'm talking here for 30 minutes, that buys you a car. This is what you have to keep in mind. And so it's not surprising that whenever you propose an instrument for an ELT, you have to be very clear about the unique discovery space in competition to other facilities that are not necessarily cheaper, but have similar problems, and you don't want to have redundant things. Also, we have the luxury at ESO to have 4 VLTs and a number of other telescopes. There will only be a couple of very large telescopes, and so there will be no PI instruments given the precious access to the telescope. You must serve a large fraction of the community. And then on one hand, you want to have low complexity to make sure the instrument works all the time, has high efficiency, is reliable. At the same time, there is, of course, a high threshold to build an instrument for an ELT. All the interfaces, all the standards you have to fulfill. So it's not like you invest 2 million and you get a simple instrument. So you have to make a minimum investment. It automatically leads then to the fact that you need a large consortium, a large team. You build only a few instruments, and necessarily the instruments will be very complex. So these are clearly two conflicting requirements. And then, of course, if you have expensive observing time, you want to sort of achieve space standards in terms of queue scheduling, pipeline processing. The data archive should be accessible to everyone and of interest to everyone, not just the observer, him or herself. So on. So these are general considerations. Another one is, of course, a constraint is the warm and complex ELT optics. Now, this is specific to the ELT. In that sense, the TMT may be a bit simpler. This is just illustrated here. I'm not going to go into the details here, but you can imagine that this leads to some of the issues. One of the issues for us is, as we're mid-infrared astronomers, we're used to classical chopping with the secondary mirror, and I'm not going to go into explaining that because I think everyone who has done observations know that you usually do some chopping as a reference, a subtraction, and then you knot between two positions to get rid of residuals that are due to the non-common path. Now, with an ELT instrument, you simply don't chop with a 4 meter or so secondary mirror anymore. And so we have been thinking of alternatives. And one option, of course, is to use an chopping mirror inside the instrument. And this is what we've done. And so within METIS, you can chop upstream. The downside, of course, is that you chop, you move slightly through the warm window and on the surfaces of the telescope. And this may lead to undesired effects. And to quantify them, I think we have to build the system. We have made some modeling. We can also consider alternative schemes like drift scanning, which have their own limitations. And there may be more. And there are many challenges in that sense. But what is clear, I think, is we have to find innovative approaches. And I have found a beautiful image. I really like that from Massimo Roberto's 2005 paper on the Ryan image. He gave me the Fitz files. I fiddled it a bit just to highlight the beauty of the extended emission. Now you have to realize this image is 5 arc minutes across, and it's a mosaic from 35 arc second frames. So you can scale it whatever you like in your Fitz viewer. You don't see really that it's a mosaic. And this is beautiful. And I think there is a lot of things in that area that we need to do and need to further improve for the challenges ahead of us. Now, another challenge, of course, is angular resolution, or the need for adaptive optics. That's very clear. If you look at the atmospheric seeing versus the diffraction limit of a 4 meter telescope, you probably can get along at 10 microns without adaptive optics. If you go to an ELT, that certainly won't work anymore, or you would give up on both sensitivity and angular resolution, so that's not what I want. So there's a huge gain in adaptive optics. However, it's not so easy to implement it for the thermal infrared. And therefore, there are different approaches. I don't want to discuss them in detail, but just to highlight the most four popular ones maybe. So you have the classical approach of just a warm AO bench in front of your telescope. You can also have a system like is proposed for the TMT, this inferior system, which is an AO system, a big container, which is actually cooled to minus 30 degrees to reduce the emission, but that helps at K-bands. That doesn't really help at 10 microns. The MICHI system has a warm AO bench, but a cold wavefront sensor inside the instrument. With the ELT, we have, of course, more mirrors in the telescope, but but we have the deformable mirror as part of the telescope. So that reduces the need to have a re-imaging AO system. Now, if you want more than just the correction from this 1 dm, of course, you have to do it. But for METIS, I think this is fine. With that mirror, we achieve almost extreme AO correction. So as you can see, there are always pros and cons the way you implement it. But one of the fundamental problems when you go cold here is that you have to pass your AO sensing light through the cryostat window, and this is just mentioned here for a zinc selenide window. You can see the transmission drops rapidly. So if you have to get all the light from your shortest wavelengths that you use for AO correction, maybe desirably even for the lasers, so you're at whatever 0.5 microns or 9 nanometers, and then you go to out to Q band, that's almost impossible to find any realistic material for a cryostat window. Okay. So now there, of course, are other optical effects, and just to mention a few in passing, atmospheric dispersion. I don't think anyone who built a thermal mid-infrared instrument has worried about that. But you can see here that already at 1 lambda over d, this gives you an offset or 3 to 4 microns. At a thinness angle of 30 degrees, you get an offset of about 1 lambda over d. And this may not be disastrous, as you can see here, for maybe the image quality in plane imaging, but it makes the use of high contrast coronagraphy very painful. Now, let me go to this one first, water vapor seeing. Have you ever heard about water vapor seeing? Well, that's probably a small effect. Due to the fact that you do sensing at 2 microns typically, or H band, K band, and then you apply the correction from that measurement to the observations at 10 microns. But this light here might be affected by water vapor that is not sensed here, that may lead to effects. Again, it's a small effect, but we need to characterize it. In the worst case, we have to ask for very dry weather when we do the high contrast mid-infrared observations. And this is not so bad because it looks like there is no correlation between the water vapor and the seeing. So this is actually good news. Then, of course, you also have to have very good cold optics. Okay. I would like to move on by just giving a brief overview of the METIS instrument, which is proposed for, which we're building for the ELT. It's one of the 3 first-generation instruments built by a large partner, large consortium of 12 partner institutions who invest a lot of effort. And this is just an image of a photo taken of the team who defended the design at the preliminary design review last year. And we hope to see first light in 2027. So I think the talks are online. I don't want to discuss the specifications here for METIS nor for MIRI in detail. This should just give you an overview of the instrument. And but the things to keep in mind, it has imaging capabilities at high contrast, of course. It has a high resolution integral field spectrograph, and everything works at the diffraction limit. And here are the point source sensitivities in microjanskis and in magnitudes for reference. Okay. Yeah, let me, in the interest of time, I'd like to skip that slide. This is, although I find it very interesting, to give you an overview of the instrument, how it is set up. You see the light coming in from the ELT here, and then we have the common for optics here that does all the beam conditioning, atmospheric dispersion correction, pupil alignment, and image derotation and chopping, and then the light is split. One part goes to the AO wavefront sensor, one goes to the imager, and then one to the high resolution spectrometer. And there's also a calibration unit. The detectors that we're using are indicated here. If you're interested in the new GeoSnap detector, there will be talks by Danny Atkinson and Michael Meyer on Friday afternoon. Now, of course, in reality, it's a bit more complicated, although even that is a simplified schematics. And I don't have the time to discuss it here, but if you want to see how that actually works, I highly recommend you go to the METIS website, which is indicated here, just METIS at Sterrewacht, Leiden University in Brandl. And then when you go to the design concept, then you will find an app here, and that app allows you to select observing modes, and then the beam builds up, and you can see actually how the light goes and what parts of the instrument become active. Okay. Yeah, we have also several coronagraphic concepts, at least 3 of them. And the reason for doing that is that it depends actually on the actual boundary conditions that we'll get with the ELT. There are concepts like the vortex phase mask who will deliver the highest contrast, assuming that we have a very stable system. Or the apodized phase mask, which is very insensitive to these perturbations, but it will not deliver the very best contrast. And then maybe if you look at something like Alpha Centauri, you start to marginally resolve the object, and then maybe that also has an impact. Of course, all that has been modeled, and I'm showing you that curve from a paper like Calumagno that was just accepted, mainly because the black line shows the nominal contrast. And then Olivier Absil has modeled all kinds of effects here that we expect to see on a big telescope. And I just picked one for illustration. Look at this here. You get, if you have 2 milliarcsecond RMS pointing jitter, yeah, doesn't sound much, 2 milliarcseconds, you already see a decrease at 3 lambda over d in the contrast of about, yeah, not just an order, not quite an order of magnitude, but it's significant. Now, what does this mean, 2 milliarcsecond jitter? Remember our 5-mirror telescope, where we have the light reflected. Here is the deformable mirror, M4. Here is the tip-tilt mirror, M5. And then, of course, you have to guide the light to the instruments on the Naismith platform here. And so, obviously, if this is a 40-meter telescope, the radius is 20 meters. So you have a long way here. If you want 2 milliarcsecond pointing jitter, that means you have to keep the beam steady here at 6.6 micrometers physically, yeah, in the focal plane of the telescope. Now, okay, this is probably not quite trivial. Okay, let me give you a very brief science overview at the end, or close to the end. So, of course, this is nothing surprising, so I don't need to dive into that. It's also, I think, very similar to the science drivers that the MICHI instrument on the TMT will have. It's the well, S-Cora set. But what I want to show you is a simulation of some of our science drivers. One is direct imaging of Alpha Centauri at 10 microns. And this is a simulation where we added 2 exoplanets, one at 1.1 AU, one at half an AU. So obviously, it's the one at half an AU. And they clearly are detected at 10 microns. Actually, this one is only the one outer there, which is probably closest to the Earth, is only detected at 10 microns. If you look at another planet in the same system, namely Proxima Centauri, and be at 2 lambda over d, we should be able to resolve that system with the high resolution integral field spectrograph and get information about the spectral signatures and the kinematics of that planet from the high resolution spectroscopy. Similarly, when you have when you use the integral field spectrograph on protoplanetary disks, and you tune the wavelengths to the CO emission at 4.7 micron. This is a model image here of the HD whatever system. And so we go for the CO line signature. And so this is obviously the model. And the IFU field of view, it couldn't be any bigger because of the angular resolution in there, but it's indicated here. So it matches just perfectly. And now overplotted is a simulation of what METIS will see of that system. And it's also interesting here that the signatures in the protoplanetary disks then, of course, are clearly revealed. In this case, there is even a circumplanetary disk. So from the accretion of gas onto the planet. So I think there will be fantastic things to be done. And now, I think I'm starting to run out of time, but of course I need to mention MICHI here. So as we know, METIS is an approved instrument. It's under construction, has passed PDR. MICHI is still on its way. It is a proposal, but I think it would be an extremely useful and complementary instrument on the Northern Hemisphere for the TMT. And so has to be mentioned here. So it is one of, I just listed the ones that have already been considered for first light. And then there is a proposed one. I suggest you see the talk by Chris Packham on Thursday. He's not going to talk about MICHI then, but he has given me the information here to present MICHI. So I think I need to advertise his talk anyway, and he will have a very interesting summary of what the general challenges is and the feedback from the community of instrument builders looking back and looking forward. So I'm looking forward to a very interesting discussion on Thursday by Chris. These are the proposed specifications of MICHI, and I also add them here just for your information. They're very many ways similar to METIS, so I'm not gonna discuss it. What I would like to mention, however, is the summary of, or the comparison of METIS and MICHI. Because of course there are many common aspects. They're all driven by similar science goals for 30 and 40 meter class telescopes. However, there are some differences. And one is that the METIS baseline is mostly sensing adaptive optics correction on the science target itself. We do not have laser guide stars in the baseline. MICHI will have. And of course, Mauna Kea is also the premier site for the thermal infrared, especially if you would want to extend beyond N-band. METIS obviously covers the southern, MICHI the northern hemisphere. METIS focuses on a unique combination of high-resolution spectroscopy and IFU and coronagraphy, which I think will be superior for the study of the kinematics and composition of protoplanetary disks. And then you can say it's an advantage that we have a design that is frozen and we move to the construction. On the other hand, if there are some breakthrough discoveries in new areas by James Webb, it's too late for METIS to react. MICHI might. And also MICHI might offer polarimetry and high spectral resolution at N-band, and I think we will get some very exciting results to hear at this conference. Okay, so that brings me to the end of my presentation. I think the conclusions are, there are definitely numerous challenges, and in the interest of time, I had to skip a few. But I truly believe that the instruments, thermal infrared instruments on the ELT will be transformational for ground-based mid-infrared astronomy. And just one piece of evidence for that statement clearly is that nowadays even ground-based infrared astronomy wins the Nobel Prize. That's probably something 10 or 20 years ago people also would not have necessarily expected, especially since Nobel Prizes are usually not given to astronomy. So also my congratulations goes to the Nobel Prize winners. But thanks very much for your attention.
Thank you very much, Bernhard. We got some virtual clapping from various people. All right, so we're 4 minutes over time, but at least not more than we have been before. Any direct questions to Bernhard? I've seen one actually in the Slack already. That was by Valentin, who wanted to ask you to quantify approximately the effect of water seeing for 7 to 8 micron at the ELTs. Not sure if this is more for you, or perhaps I see Olivier is also online, but I'll leave it up to you.
That's a very good question, but I would have to think about the answer.
So, since Olivier is also there, and I think
I think the short answer, of course, Olivier can give a more detail. Is we're studying that. We're studying that with METIS and other mid-infrared interferometers. The good news and the bad news is that the effect is not noticeable at 8-meter telescopes. So you need longer baselines to see the effect. Sorry, Olivier, if you want to add.
Yeah, I do not have a sufficiently robust estimate at this point, but the ballpark number is that the contribution of water vapor seeing to a single conjugate AO system will be about twice as large as the residuals from the AO itself at N-band. So in principle, we should be dominated by water seeing in standard conditions for an ELT class telescope, but this is something I'm trying to figure out with more data coming from the METIS interferometer at the VLTI. So that's, well, stay tuned.
All right, a second short question. I don't see any raised hands, but Tane Curry has raised one on Slack. I'm just going to read it here. What about the impact of adaptive secondary mirrors for M and N band high contrast imaging like on the LBT? How much better would the performance be for a METIS-like system? I think we've seen the curve, but Bernhard, do you want to comment on that briefly?
Not really. I think there are so many plots. Actually, what I would invite you all, if you have specific questions, please send them on the Slack channel, and I may be able to provide you with a figure. Because it's always, especially now, I mean, in a face-to-face meeting, you could go back and show the slides and with the pointer, it's all a bit more cumbersome here. I'm happy to show you or send you some plots if you send specific questions.